So first thing, how many people noticed that the points did not add up to 100? All right. So should have done the counting unit first. So my bad, it only added up to 85 points, and so you didn't get your induction question. I'll hand them out at the end. So you didn't get your induction question, which is kind of a bummer because, one, I know you were looking forward to the induction question, and I know that because some people managed to use induction on some of the other questions. It was an accidental oversight. I may do a quiz sometime between now and the final just to make sure people have nailed down induction, because I don't want the exam to be the first time you're really tested on it. But that's okay. So we tested all the other stuff that needed to be tested. So let me go ahead and make some comments on this. So it was graded out of 85, and then I scaled it up to 100%. So your percentage grade in Canvas, and at the end is out of 100. So question 1 was on set theory, so doing some set operations. No major issues there, except when we do this subtraction, right? This is not a division operation. I've still got a few people who are dividing numbers in one set from another. That can't be what this means because sets don't always have integers in them. So this is a subtraction. This is A, take away B. So take all the things that are in A, throw away anything that's in B. Okay, so this will be a subset of A. It'll be exactly the subset where there's nothing in there that belongs to B. The power set, so the power set of a set is what? It's all the subsets, including the null set. So if A is equal to, say, this set, what are some of the things in the subsets? Well, certainly A is a subset of itself, so that's in the power set. Certainly this is a subset. So is this. So is this. And there's a whole bunch of subsets you can come up with that will all be in the power set. This is a subset. It's the empty set. It's the same thing as this, the set containing no elements. So either of those, if you had written them, would be a subset. Those are in fact the same thing. But this is not part of the power set of A. This thing on the left, this is not the empty set. Okay, this is a set containing one thing. The one thing it contains is the empty set. Okay, but that's not part of the power set. Right, because the empty set is not an element of A. The empty set is a subset of A, but it's not an element of A. That's a really subtle distinction. Okay, this is actually a set. This is a set. It contains only 5 things, 1, 3, 5, 7, and 9. Did we name the empty set? No, so it's not a member of A. Okay, since it's not a member, this cannot be part of the power set because it's not a subset. So how many elements are in the power set? That's 32. This is this rule that we talked about. The cardinality of the power set of A is equal to 2 raised to the number of things in A. This is for A finite. We can prove that using induction if we want. I think we might have already done that. All right, second question, modular exponentiation. I didn't work this one through until I had already given the exam and I was making my grading key up here. This took a lot more calculation than I expected. So I cut you a lot of slack on the calculations. Okay, I told some people you probably wouldn't need a calculator for this, and then I had you doing these computations. But here's the basic idea. So 5 to the 262 modulo 37. To use modular exponentiation, you want to note that 262 is 256 plus 6, which is 4 plus 2, right? You write it as a sum of powers of 2. And then 5 to the 262 is 5 to the 256 times 5 to the 4th times 5 squared. If you added these, you lost a point. Okay, you got to multiply. That's law of exponents. And then to calculate each of these, you do this repeated squaring. So 5 to the 1st is congruent to 5. 5 squared is 25. 5 to the 4th is 25 squared, which is 625. And you have to reduce that modulo 37. And here's where you needed to start doing some calculations. So this turns out to be 33. If you made math errors here, or if you didn't get all the way through it, I didn't take off points, okay? Because I meant for these numbers to be numbers that worked out nicely, and they weren't. So this is also minus 4. 5 to the 16th would be minus 4 squared, which is 16, and you keep going. And when you're done, you end up with congruences for these three things. You multiply them together, and your final answer turns out to be 30. But like I say, I didn't take off for math errors. As long as you started off right, you were doing repeated squarings.
And 5 to the 16th, shouldn't that be congruent to negative 4 to the 4th?
Oh, yeah, my bad. 5 to the 8th. And then 5 to the 16th is 256. And keep going. Thanks. All right, question 3 says use modular arithmetic to show clearly, boldface, that the product of any 3 consecutive integers is divisible by 6. And I gave you a hint. Consider doing this by breaking it into 6 cases and working mod 6. All right, most people had the right gist. Okay, they wrote down 6 cases or 5 cases or 7 cases in some cases. And I saw things like this. 0 times 1 times 2 is congruent to 0. 1 times 2 times 3 is congruent to 0. 2 times 3 times 4 is congruent to 0. And that's good. That's the intuition that we're after here, right? So I'm happy to see that, right? And in some cases, people said, 1, 2, 3, right? So you clearly understood the idea of this proof. But there's 3 things you got to do here. You got to have the intuition, okay, which most people had. And then you've got to structure it in some kind of formalism. And then you got to dot the I's and cross the T's, right? You got to make it rigorous. So let's talk about the formalism here. What's this idea of proving things by cases, right? Because this by itself is not a proof. You've written the number 1 and said 0 times 1 times 2 is congruent to 0. What does that prove, right? How does that relate to the product of 3 consecutive integers being divisible by 6? So here's an example of a proof by cases. Okay, so given the following class schedule, so let's say you have data structures on Monday and Wednesday, and you have physics on Tuesday and Thursday, and you have CSE 215 on Friday, and you have yoga on Saturday, and you have basketball on Sunday. Okay, this is your schedule at Clark. Prove you are at Clark every day. Okay, how do we prove you're at Clark every day? We could take every single day, right? This is an infinite long quarter, by the way. So we could take every day from here till the end of time, and we could say, okay, so, January 17th, 2530 is a Tuesday, and on Tuesday you have physics, so you're going to be at Clark, right? And we could do that for every single day, but it would be a really long proof, because we need a line like that for every day from here out to the end of time, right? So we can break this into cases. And what are our 7 cases? Any day is either Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. That's the modulo 7 thing, right? Any day that you can think of is going to be either Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. Just like any number is going to be congruent to either 0, 1, 2, 3, 4, or 5 mod 6. Okay, so whatever day you give me, I know that exactly one of these things is true. The day is Monday, Tuesday, Wednesday, Thursday, etc. And now you argue for each of those possible cases. If today is Monday, you have data structures, you're at Clark. If today is Tuesday, you have physics, you're at Clark. If it's Wednesday, you have data structures, Thursday physics, Friday discrete, Saturday yoga, Sunday basketball, you're at Clark. Since whatever day you pick, it's going to be one of these 7 cases, and in each of those cases we've proven you're at Clark, we can conclude you're at Clark every day. Okay, that's a proof by cases. That's all we're doing here in a question like question 3. So question 3 says for any integer, if you multiply it by the next integer, the product's divisible by 6. And we don't want to do this for every single integer, so we break it into cases. And we say there's 6 possibilities. For any n contained in Z, n is congruent to 0, 1, 2, 3, 4, or 5 modulo 6. And we know that because we know the division algorithm. We know that we can always find a congruence modulo 6 somewhere between 0 and 6 minus 1, 5. And so now we just have to show that for each of these 6 cases, our statement is true. So now we can state case 1. And what is case 1? N is congruent to 0 mod 6. You got to say what case 1 is, right? Listing 6 cases doesn't tell you how that relates to an arbitrary integer, right? So case 1 is the case where n is congruent to 0. And we're trying to show that n times n plus 1 times n plus 2 is divisible by 6. So I would write something like n times n plus 1 times n plus 2. And let's look at its congruence. It's congruent to 0 times 1 times 2, which is congruent to 0 mod 6. Case 2, n is congruent to 1 mod 6. N times n plus 1 times n plus 2 is congruent to 1 times 2 times 3, which is congruent to 6, which is congruent to 0 mod 6. And you keep going. And after the end of the 6 cases, you've shown that in each case, this product is congruent to 0. Right? And simply stating something like 3 times 4 times 5 is congruent to 0, how does that relate to your number n? Right? I understand what you're trying to say here. That's the intuition part, okay? That gets you most of the points. But this by itself has nothing to do with n unless we say n is congruent to 3, and then n times n plus 1 times n plus 2 is congruent to 3 times 4 times 5. And now you can say that's congruent to 0. Therefore, you've shown this is divisible by 6. Got the idea? So it's details, right? And I want you to have the intuition for this, okay? And most people were able to show that. So that's the biggest piece of this. And then it's formalizing this, and then just sort of, minor details, making sure that you show what n is in each case, make sure you mention modulo 6 and things like that. All right, so mostly good credit on that. Question 4. So this was a full-on proof question. Given 2 integers a and b, prove that if a, b is odd, then a is odd or b is odd. Okay, given 2 integers a and b, prove that if a times b is odd, then a and b are each odd. This is an AND. Prove that A is odd and B is odd. Okay, start with some propositions. Most people did not start with a proposition. They started with definition of odd or something. So let P be the proposition A times B is odd. And we're trying to prove the proposition that A is odd and B is odd. So we could let Q be the proposition A is odd and B is odd. Or you could make two propositions and try to prove their conjunction. But first order, right? So prove if P, then Q. And I think if you start with this, you're less likely to accidentally do something like proving this, which is a totally different statement. And it's pretty straightforward to prove that if A is odd and B is odd, their product is odd. Right? This is 2k plus 1, this is 2j plus 1. You multiply them out, you're going to get 2 times something plus 1. And it's even easier to prove this, and about half the class proved this. Right? But if you know that this is what you've proven, you're not going to make the mistake of proving that and thinking that you're done, because it's very clear when you write this out that this is what you need to prove. But nonetheless, I got proofs which said, suppose A times B is odd, stuff, 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 therefore A times B is odd. Or suppose A is odd and B is odd, stuff, 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 therefore A is odd and B is odd. And what they proved was if Q, then Q. So the reason that I keep harping on writing out clear propositions is not just to give you work to do, right? It's to help you avoid doing things like this. All right, so this works well with an indirect proof. Okay, what we're allowed to do is prove that not Q implies not P. We can prove the contrapositive. And once we know this, we can say, therefore, if P, then Q. So what is not Q? Well, it's the negation of something and something. De Morgan's theorem, this says A is even or B is even. Okay, because Q is saying A and B are both odd. The negation of that is that at least one of them is even. Doesn't have to be both, just one. If A is even, then you can't say A and B are both odd. So if we start with this, we can write A equals 2 times K, B equals 2 times J. Different variable here, right? You can't say B is also 2 times K, because now you're saying B is equal to A, and we don't know that. So A is 2K, B is 2J. Now we can multiply these out. And A times B will be 2 times K times J, which is 2 times, some integer. Therefore, AB is even. Therefore, we've proven that P is false. So that's the essence of a proof by contradiction. We negated Q, and we proved that P was also false. So now we know this, and now we just take the contrapositive. We've got if P, then Q. But our usual language of proof by contradiction is say, suppose that this conclusion is not true, so A and B are even, so this is the case, and then we get AB is even, which is a contradiction. But yeah, it should be an or, right? So let's break this into cases, right? Because what I've done here is I've assumed that A is even and B is even, okay? But it's actually a disjunction. So we've actually got two cases. So case 1, A is even. So A equals 2k. So A times B equals 2 times k times B equals 2 times some I1. And therefore AB is even, therefore not P. Case 2, B is even. So B equals 2 times J. So AB equals 2 times A times J, which is 2 times some other integer, and therefore AB is even. All right, so if you were on the right track, you got bunches of points. If I saw something like 2k or 2k plus 1 in there, and you were working logically, right, you got credit for that, because again, that's the intuition, right? The intuition is if these numbers are both even or one of them's even, the product's going to be even. So we work backwards from there. Greatest common divisor. So most people had this fine. 1530 equals 1 times 1088 plus 442. 1088 equals 2 times 442 plus 204. 442 equals 2 times 204 plus 34. And then 204 equals 6 times 34 plus 0. This is your GCD, okay? The thing you're multiplying by has nothing to do with your final answer. It's all about the remainders. Okay, so this is your GCD, and you can divide those in to double check and make sure you're getting a divisor. So a couple of points if you use the 6 instead of the 34. 1 point if you made a math error, but most people had the right idea here, so nothing too worrisome there. Congruences. So I wanted congruences between 0 and n minus 1 for question 5. So 25 is congruent to what mod 7? 21 is a multiple of 7, so you've got a 4 left over there. So 25 is congruent to 4. 19 is 1 more than a multiple of 6. That's 18. So 19 is congruent to 1 mod 6. All right, negatives. Negative 10 is congruent to what? Mod 3. Well, it's congruent to a lot of things, right? It's congruent to negative 7, negative 4, negative 1, 2, 5, 8, 11, and so on. But the answer we want is the number between 0 and 2, so it's this number right here. Right? And the test is this minus this should be divisible by 3. That's the other way to look at congruence. A is congruent to B if their difference is a multiple of 3 in this case. So minus 10 minus 2 is minus 12. That's a multiple of 3. Or 2 minus negative 10 is 2 plus 10, 12. That's a multiple of 3. So your answer here is 2. So 10 gazillion is congruent to what modulo 1,000? Well, you don't have to work too hard to divide this by 1,000. Boom, boom, boom. It goes in an even number of times. This is congruent to 0. In other words, it's divisible by the moduli, 10,000 in this case. All right, 7 is congruent to what? Modulo 81, 661. And I got some interesting answers on this one. I got some 6s, and I got some big numbers. What do you get when you divide 7 by this big number? Yeah, you get 0 with a little bit left over. How much is left over? 7. And that's a general property. Small number modulo big number is always congruent to small number, right? We know every number is congruent to itself. And here we're looking for a number between 0 and 81, 660. So 7 works fine for that. And then for F, big long number ending with a 7 times big long number ending with an 8. modulo 10. And we looked at this when we were casting out 3s and 9s and 11s and so on, right? This big long number ending in a 10, ending in a 7 is congruent to 7. And this big long number ending in an 8 is congruent to 8. And so their product is congruent to 56, which is just congruent to 6. So that was a one-pointer. All right, true-false questions. So A divides B and B divides C implies A divides C. True or false? Totally true. Right? This is saying that B is a multiple of A and C is a multiple of B. And since B is a multiple of A, C is definitely a multiple of A, which is what A divides C means. Division algorithm is used to find the greatest common denominator of two numbers. That is false. Division number tells us that when you take things modulo n, you can find a unique number between 0 and n minus 1. Okay, Euclid's algorithm finds the greatest common denominator of two numbers. Although some people said, true, this is Euclid's algorithm. So I gave credit for that. If p is a prime number, then p plus 10 can never be prime. True or false? False. 3 and 13 is a good example, right? There's no reason that p plus 10 couldn't be prime. In fact, there's no reason that p plus any even number couldn't be prime. All right, Goldbach's conjecture relates to the existence of even prime numbers. That is false. Goldbach's conjecture relates to writing an even number as a sum of two primes. Nothing to do with even prime numbers. There is no theorem about even prime numbers. We know there's exactly one even prime number. What's that? That's 2. That's the only even prime, because any other even number is divisible by 2. And there's an infinite number of primes greater than that weird expression 2 to the such and such minus 1. That's totally true, because there's an infinite number of primes. And if there was no prime bigger than this number, there could only be this many primes, which is not infinite. So that's definitely true. All right, so any questions? So we're going to go on to counting. And permutations, combinations, binomial theorem, pigeonhole principle. We're going to try to get through all of this in the next few days. This is your homework on Thursday. If there's stuff we don't get through, then I'll excuse those questions on the homework. But I think we'll get through everything in the next couple of days. And then next week, I think we're going to start talking about formal languages and automata theory, because I definitely want to get through that material. And then if there's time left at the end, we'll double back and we'll pick up some stuff on recursion and recurrence relations and possibly some graph theory. But we'll do some of that stuff in 223. So, but let's talk about counting this week. So, counting is a simple thing, right? You just count things. It tells you how many of something there is. What we're going to talk about are some rules that we can use to count things in very particular ways to answer questions. This is going to lead us into things like combinations and permutations and probability theory. So let me start with something called the product rule. So here's what the product rule is. This relates to the number of ways to accomplish some task. So given a task T, which can be broken down into subtasks, and we're going to start with two subtasks, T1 and T2. done in succession. So we've got some task we're trying to do. We can split it into two tasks, T1 and T2, such that first you have to do T1 and then you have to do T2. So if T1 can be done N1 ways, and T2 can be done N2 ways, then T can be done N1 times N2 ways. That's the product rule. Mm-hmm. For example, suppose we want to have two people sit down in a room with 20 desks. How many ways can we seat two people in an empty room with 20 desks? And we're assuming that each person has to sit by themselves. They can't both sit in the same desk. So our task T is to have two people go into a room and take a seat. And we're going to break that into two subtasks. T1 is the task of taking the first person, sending them into the empty room, having them pick a seat. T2 is then having the second person go in and take an empty seat. So T1 is where the first person picks a seat. Okay, how many possible ways can that first task be done? 20 ways, because there's 20 empty seats in the room, and to accomplish this task, the person has to choose one of those 20 seats and sit down. So there's exactly 20 ways that first task can be accomplished. After T1 is done, now we execute T2, which is second person picks an empty seat. How many ways can that be done? That's only 19 because one of the seats is occupied. So T2 can be accomplished 19 ways. So according to the product rule, T can be done 20 times 19, 380 ways. So there's 380 ways to sit two people in an empty room. Mm-hmm. Yeah, this is all probability related. So suppose that these seats had the capacity for two people to sit in one seat. So there was no restriction on the second person. How many ways could T2 be done then? That could be 20, and so the total task would have 400 ways to be solved. So it depends on the problem. It depends on the specifics of the problem. All right, so how many student IDs are possible where student ID is 2 letters plus 1 digit? And there's no restriction on which letters you use. Any 2 uppercase letters from A to Z followed by a digit 0 through 9. So T is the task of picking a student ID. And we can split it into 3 subtasks. T1, pick the first letter. T2, pick the second letter. T3, pick a digit. So how many ways can we pick a letter? And how many ways can we pick the second letter? Still 26. And how many ways can we pick a digit? 10. So the total number of ways that we can pick a student ID is 26 times 26 times 10. Therefore, that's the number of possible student IDs. Make some sense? Suppose our task is to pick an ordered set of 4 bits. So bit 0, bit 1, bit 2, bit 3. We want to pick exactly 4 bits in a particular order. We can split this into 4 subtasks. T1, pick the first bit. T2, pick the second bit. T3, pick the third bit. T4, pick the 4th bit. How many ways can we choose a bit? It's a 0 or a 1. How many ways can we choose the second bit? And the third and the 4th? 2 ways each. So the total number of ways that we can choose a 4-bit number is 16. Does that result surprise anyone? Right? We know that there's exactly 16 4-bit numbers. If you make a 4-bit truth table, it's got 16 rows. If you have an integer with 4 bits, it can go anywhere from 0 to 15. But this is really just a consequence of the product rule. Right? That's just another way to get to the same thing. Suppose our task is to construct a truth table for some function with 4 input variables. So we have I0, I1, I2, I3, and we have our function f. How many possible truth tables can we construct? Well, if we think about this truth table, how many rows are there? 16 rows. So if our task is to construct a truth table, we can break this into 16 subtasks. T0 pick the bit to put into the first row. T1 pick the bit to put into the second row. T15 pick the bit to put into the last row. How many ways can we pick a bit? We've got exactly 2 choices for each. So the total number of truth tables would be 2 to the 16th. So 65, 536. Lots of truth tables. And if you had n input variables, you would have 2 to the n rows. And for each of those rows, you could do your task in one of 2 ways. Pick a 0 or pick a 1. So we would have 2 times 2 times 2, a total of 2 to the n times. So 2 raised to the 2 to the n. That's the number of truth tables of n input variables. So that grows really quickly. Got the idea? Suppose we have a deck of 52 cards, so every card is different from every other card. 52 cards and we shuffle them up, right? How many possible arrangements? Are there? How many different ways can we arrange 52 cards? So our task is to come up with an ordering of these 52 cards. What's our collection of subtasks? What's our first subtask? Pick the first card, right? Yeah, so first subtask is pick the first card, and then pick the second card, and then pick the third, and pick the fourth, and finally pick the 52nd card. So we can just say that process of coming up with an ordering of these cards is picking the card that's on the top of the deck, and then the second one, and the third, and so on. And the number of ways that we can choose which card is on the top of the deck is 52, because we got 52 cards in the deck. We're going to pick one of them and say this is going to be the top card. But once we've done that, and we want to pick the card to be in the second position, we only have 51 cards we can choose from. And when we get to the last card, the card we're going to choose to put on the bottom, we're only going to have one card to choose from. There's only going to be one card that's not in the deck. So the total number of ways we can do that is 52 factorial. So this is where factorials start to kick in with all this stuff. All right, given two finite sets, M and N, where the number of elements in big M is little m and the number of elements in big N is little n, how many functions f from m to n exist? So how many different functions can we find from one set to another? Any kind of function, long as it's a legal function. So how can we break this question of creating a function into subtasks? Break it down into steps. You're right, but
Start with the visual proof, maybe. How many functions?
so let's
Yeah, you could start with the sets using n plus a constant.
so let's name the elements in our sets. So the elements in M are M1, M2, M3 up through M sub M. And the elements in N are N1, N2, N3 up through N sub N. So what does it mean to have a function from M to N?
Everything from n ties to something in n.
Everything in M maps to something in N.
So a better first step might be to take everything in m and assign it to 2 and 1. That would be,
Okay, that would be one function.
and then maybe the step would be to do that for each n.
Okay, that would give you N functions.
Yeah.
Where would you go next? So you're thinking about it the right way.
So I know there's one where it's a 1. No, there could be many where it's
Could be many where it's one-to-one.
how would we get?
Think about it backwards from what you're thinking right now. Is this another way to define a function? Right? If we define what f takes m1 to, what it takes m2, what it takes m3 to, and so on, that'll fully define the function. All we've got to do is say what its value is at each of these points. So if we simply say what f of m1 is, and f of m2, and f of m3, for all the m's, that will completely define our function. So these are subtasks. And how many ways can we map f of m, can we map m1 to something in n? Right? It could go to n1, n2, n3, or n. So there's n ways to do this, and there's n ways to do this, and there's n ways to do this. So it's n times n times n times n, a total of m times. So n to the m possible functions. Now if we want it to be injective, m1 can map to n possible values, but m2 can only map to n minus 1, right? Because it can't map to the same thing that m1 mapped to. And m3 could only map to n minus 2, and so on, and so we'd actually get n times n minus 1, a total of m times. And if we wanted to be surjective, it'll put even more restrictions on it. So lots of applications of the product rule. Okay, I think you got the idea of it. So what we want to talk about tomorrow is the sum rule, which is for doing tasks where we can do one task or another. And then we'll talk about a subtraction rule. And then we'll talk about pigeonholes, and then we'll come back to permutations and combinations. Okay, so we will start from there tomorrow. All right. Yep. Hey, what's your last name? Yeah. Yep. Yep. There you go.
Thank you. With this, are you saying like I missed a step, or did you really just not understand that?
No, I understood what it was, but in the proof, you're not telling me what this is.
Okay.
Right, so you said n is congruent to 0, 0 times 1 times 2 mod 6 is congruent to 0. What does this have to do with n?
This one, but I could have written that clearer. But I could have also step 5 there. It's just the only one that isn't crossed out. I'm afraid that wasn't super great. Just 5 here at the top.
Yeah, that's okay.
I should have written that.
Let P of A be the
clearer.
proposition a times a plus 1 times a plus 2 is divisible by 6.
And so,
Which is congruent to 0, right. But, so A is 0.
P of A in this case, or P of 0 in this case.
Yeah, P of 0
Yeah, okay.
says 0 times 1 times 2 is divisible by 6, which is congruent to 0. So that is, yeah.
That would have done it.
Yeah.
Okay.
Hey.
You took 6 points rather than 5. 6 questions, not 50.
Yeah. So C is 3 points, E is 3 points.
Oh, this one 1.
This was
Okay.
1 and D was 2.
Oh, okay.
Yeah.